Today we'd like to take our study of force friction one step further and look at stopping distance. This is one of two reasons why we study force friction in the first place. For this level of physics student, we want to make sure that you're able to calculate how much distance is required to stop an object. And also later, we're going to be looking at how quickly we can go around turns without having our car slide out of the roadway and potentially get into a lot of trouble. Okay, so stopping distance. How much distance is required for an object to stop? Okay, it all comes back to this picture that you had in your last set of notes, so you don't have to redraw it. I just want to remind you the steps that you're going to go through. Step one is you find the force of gravity. If you're on Earth, just use 9.8 times the mass. If you're on a different planet, use the gravitational field of that planet. And if you don't know the gravitational field, you have to use the longer gravity equation. Once you get the force gravity, you're going to set it equal to normal. The force down and the force up on the object are almost always going to be equal on a level roadway. Then what you're going to do is find the force friction. Remember that the force friction comes from the linear graph, and that the formula is friction equals the coefficient times force normal. That's why we need the force normal, so that we can find the force friction. Remember, the coefficient is determined by the type of surfaces that are involved. You get that off of your reference sheet. All right? So here is our situation. We've got our car, and our car is going to be moving along the roadway, and then at some point the car is going to jam on the brakes. We want to know what speed the car is going when the driver applies the brakes. They're going to do it when they hit this zero distance to the braking line. So they hit it, the car starts slowing down. You can see it's now down to about 35 meters per second. It's gone somewhere around 25 meters. I want to know how far is it going to travel before it comes to rest completely. Okay? So set yourself up this problem. This is real important because this is how you're going to tackle all the problems. Okay, so step one, you find the force gravity. It tells us that the mass of our car is 1,119 kilograms. Multiply that by 9.8 and get your force gravity. Force normal will be the exact same value. So whatever value you had for force gravity, put it in as your force normal. Okay, then you're going to use your friction equation. It tells you that your surface is a dry road with new tires. So you want to look on your reference sheet. You want to find dry roadway with your tires. Because the tires are new, we're going to go with the highest possible coefficient of friction. If the tires were in bad shape, we'd go with the lowest value. And if it doesn't tell us, we go with the average value. So we're going to use 0.8 times whatever we had as our force normal. That gets us our force friction. The friction is the one that is trying to stop the car. There is no force tension pulling forward. It's just the momentum of the car that's trying to carry it forward, because objects in motion stay in motion. So then we go to Newton's second law. Force net over mass. The net force is just friction. Friction is the one that's slowing the car down. Gravity and normal are equal, but they're in opposite directions, so they cancel. We had to find them so we could figure out friction, but we don't need them when we do force net. So you take your force friction, you divide by the mass of the car. You get the acceleration of the car, and you put it into your list. It's important to make it negative because it's slowing the car down. Okay, once you have that, you go back to your initial velocity, and hopefully you remember that our car was traveling at 40 meters per second when we hit the brake. We want to keep going until the car stops, so we make our final velocity 0. I'd like you to pause the video and finish this calculation. I'd like you to figure out how much time it took the car to stop and how far did it travel along the roadway before it came to a complete stop. Okay? So again, find gravity, set it equal to normal, get friction based on normal and the road surfaces. Use your Newton's second law equation with friction as the stopping force. Get that acceleration, make it negative because you're slowing down, and put it into your list. In this case, we know the starting speed, we know the speed we want to end at, so we should be able to work through this problem. Okay, I want to show you a video. So this is a great little video talking about how your stopping distance is affected by how you drive and the conditions of the roadway. This is a matter of life and death. There are times you're going to be driving in dangerous situations, so I would like you to listen carefully to what this person has to say.
Whether you're going back and forth from work or driving to actually go get a view of that great fall color, you know the weather is always a factor, even on a sunny day. So we're going to talk travel because in the fall there's a complicating factor, and that is the leaves. Let's take this car out into reality or augmented reality and talk about how the weather impacts your travel. Now, even when there is no weather falling from the sky on dry conditions, it takes about 80 feet to stop your car if you're driving at 45 miles per hour. And that, of course, is dependent on what kind of tire tread you have, what kind of road conditions they're like, but still 80 feet. Now let's factor in the weather. And, you know, when you've got these great leaves on the trees, you know the color's gorgeous, but all of a sudden they're going to come down and they'll cover up the roadway. They'll cover up any potholes or any bad road conditions that are out there. And also when it starts raining, now we got some complications. So the rain falls, you've got your wipers on, you've got your headlights on, of course, if your wipers are on, and now the leaves start getting wet. And you've heard the saying that wet leaves are slippery as ice. Well, indeed they are. Why is ice slippery? Well, there's actually a film of water right on top of ice. Same thing happens actually with your car's tires on these leaves. So take a look. You've got the car's tires that are hitting the leaves, and the leaves are on top of the road. Leaves have a waxy coating on both sides of them, and that actually repels water. Trees get their water from their roots, right? Not from their leaves. So the waxy coating repels water. That makes leaves very slippery. And leaves slip on leaves slip on the road. Your car's tire slips on the leaves. And when there's layers of these wet leaves, the slick factor is exponential. You try to brake on this, you see the swerve, right? All of a sudden, you more than double your stopping distance if you're traveling at 45 miles per hour. And that's not a clean stop, is it? So if you're traveling, even if it stops raining and you've got leaves on the road, you know that it takes hours for wet leaves to dry out. You need to slow down, both hands on the wheel. Make sure you have some good tire tread on your car, and make sure you stay vigilant, because even when it's not raining, when you've got leaves on the roads, it could be slick as ice, especially if they're wet.
Okay, next I'd like you to look at our Malachi, that's my cat, sliding across my Flyers rug in my living room. And there he goes. And what we'd like to do is we'd like to figure out this time, we know how much distance it took to stop. We'd like to figure out the coefficient of friction of two surfaces that are obviously not on our reference sheet. So here goes Malachi again, chasing after the laser pointer. He gets onto the mat slides a certain distance, and then comes to rest. All right? So this time you're going to be working it backwards. So what we do is we start with the stuff that we measured. So Malachi was moving at an initial speed of 2.7 meters per second. The mat slid 45 centimeters. Make sure you put it in meters. The mat eventually stopped moving as friction took away all of the momentum of the mat. You find the acceleration. So it's working backwards from what we did last time. You then take that acceleration, you put it into your Newton's second law, realizing friction is the force that's stopping you, and you solve it for the force of friction. Okay? The cat has a mass of 5.2 kilograms, so that goes in as your mass. Whatever you got here, you plug in here. Now note, your acceleration will be negative, but just make it positive when you plug in. Once you got your force friction, you plug it into your force friction equals coefficient times normal, and you get force normal by figuring out the force of gravity of the cat and setting it equal to force normal. So we are trying to figure out a coefficient of friction based on experimental data, and that is the only way we can figure out coefficient of friction. Every one of these coefficients that ever has been found in this manner. Experimental data. Here's another example problem you could try. This one is the way the cops would try to figure out how fast you were going based on the length of your skid marks. So this time, you're going to know how far you skidded based on the skid marks. 60 feet, so about 18 meters. You know you stopped. Actually, in this case, they hit another car, so their final speed was about 20 miles an hour. So we're going to change that to meters per second. And your goal is to find the initial speed. So you go through the same process. Force gravity, set it equal to force normal. Find the force friction. Put it into Newton's law. It seems like a lot, but it's a very common process that hopefully you'll get really good at. It tells you the mass of the car is 1620. And it does not tell us exactly what we're doing here, but it says we have average tires and dry roadway. So you're going to assume the average coefficient of friction. So the worst would be 0.5, the best would be 0.8. You want to use a coefficient right in the middle of those two. Okay, so this is how we deal with stopping distance. Gravity, normal, friction, Newton's law, equations of motion. Everything you've ever learned in one little package. All right, sometimes you work forwards and sometimes you work backwards.